You ever feel like, dealing with IT infrastructure is like trying to wrangle a bunch of mismatched parts together, hoping they'll somehow work? Like you're constantly stuck clicking through consoles and every little configuration difference just waiting to blow up in your face?
Oh, yeah. It's like a recipe for disaster waiting to happen, right? Endless nights trying to figure out where someone went wrong, a constant battle against inconsistency. So the idea of a better way, a more streamlined way to manage it all, well, that's pretty appealing to anyone who's been there. And that's where this idea of infrastructure as code comes in. Instead of manually wrestling with servers and networks, we start treating our entire IT setup like code, using machine-readable files to define everything.
It's like finally bringing those software development best practices to the world of infrastructure, right? Think version control for your server setups. Imagine collaborating on network changes just as easily as you would with code, and the ability to automate entire environments from scratch. It's not just about making things a bit easier, it's really a fundamental shift in how we think about and approach IT.
And leading the charge in this space are tools like Terraform. So in this deep dive today, we're going to unpack the core ideas behind coding infrastructure with Terraform. We'll be using the learning path you provided as our guide, trying to give you a solid grasp of how this all works in the real world.
Exactly. We'll be looking at the big wins of using IAC with Terraform, the actual nuts and bolts of getting it installed and set up on your system, then the key concepts that make Terraform tick, things like the HashiCorp configuration language, providers, resources, and stater. And finally, we'll look at how to leverage Terraform modules to create clean, reusable, well-organized infrastructure code.
But more than anything, we want this to be clear and digestible. No need to get overwhelmed. We'll be breaking these core concepts down step by step so you can really see how Terraform can bring clarity and a whole lot more efficiency to how you manage your infrastructure.
So let's get into the why of all this.
Yeah.
Why should someone even consider this shift to infrastructure as code, and how does Terraform help make it happen? The sources we have here really highlight some pretty compelling reasons.
What's really game-changing is the sheer speed and agility that IAC brings to the table. Imagine spinning up entire environments for development, testing, and production with a single command. No more manual provisioning, you just hit go, and Terraform does the heavy lifting. This dramatically speeds up everything from development to deployment, which is huge. You can react to market changes way faster than those who are still stuck in the manual world.
It's almost like the difference between building a machine piece by hand and having a blueprint that lets you perfectly assemble it every single time, right? And the sources really stress this idea of rapidly creating entire infrastructure architectures through scripts. That consistency is huge, because it means you can eliminate those pesky inconsistencies that can creep up between different stages of your deployment pipeline.
Precisely. And when you standardize your setups like that, using IAC and Terraform, you're not just making things faster, you're making them more reliable. Applications run smoother, things become more predictable, and you can drastically reduce the administrative headaches of keeping everything up and running. Define it once, automate it, and you drastically reduce the chance of configuration drift and those little errors that can cause so much trouble.
One of the things that really stood out to me in the sources was the disaster recovery aspect. The idea that if something goes wrong, you can rebuild your entire infrastructure from code.
Yeah.
That's powerful, adds a whole new level of resilience, and makes those potential outages a lot less scary.
Absolutely. And let's not forget the security implications. Automating security configurations across your entire infrastructure means less room for human error. You can ensure that your security policies are applied consistently without relying on manual checks and balances.
It's clear we're seeing a real paradigm shift happening here. Infrastructure management is moving away from that old manual reactive model towards a more proactive software-driven approach. It's all about taking those core software engineering principles and applying them to infrastructure to achieve more scalability, more reliability, and a lot more operational efficiency. And Terraform is a tool that's really making that shift a reality for a lot of people.
It is. Terraform provides a calming language and a really powerful framework to put these IAC principles into practice, and it does it across a wide range of cloud providers and services.
Okay, so let's say you're convinced and ready to dive in. The very first step is getting Terraform installed on your local machine. The process is going to differ a bit depending on whether you're on Windows, Mac OS, or Linux, so let's walk through each one.
The heart of this is getting the Terraform CLI onto your system. This is the tool you'll use to interact with Terraform, to execute commands to do the actual work.
Let's start with Windows. You want to head over to the official Terraform website and grab the right ZIP archive for your system. Make sure to choose either the 32-bit or 64-bit version, whichever matches your system's architecture. Once it's downloaded, extract the contents of that zip file to a folder, anywhere you like. A straightforward place, easy to remember, is something like C Terraform.
Now, this next bit is super important for Windows folks. Updating your system's path environment variable. The reason this is so crucial is that it lets you run the Terraform command from any command prompt or PowerShell window. No need to navigate to that C Terraform directory every time.
You got it. Basically, you need to add that directory where you extracted terraform.exe, for example, C Terraform, to your system's path. Once you've done that, the simplest way to test it out is to open a new command prompt or PowerShell window and type in Terraform D version. If you see the installed version of Terraform printed out, you're good to go.
All right, let's switch gears to macOS. The recommended and usually the simplest way to get things set up here is to use Homebrew if you have it installed. Homebrew is a fantastic package manager for macOS, makes installing a lot of developer tools a breeze.
It's a lifesaver, for sure. Now, if you have Homebrew set up, the first command you'll run is brewtap HashiCorp-tap. That tapping thing, think of it as telling Homebrew about a new source, in this case, HashiCorp's repository where it can find packages. It's like adding a new app store, basically, to your system.
Once you've tapped that repository, installing Terraform is just a matter of running brew install HashiCorp tap Terraform. Homebrew will take care of the download and installation for you. To check if it worked on macOS, run Terraform version. Notice the double hyphen there, a little quick on macOS.
Good catch on the double hyphen. The sources do mention an alternative for macOS, though, a manual installation. For that, you download the Terraform package straight from HashiCorp's website, similar to how we did on Windows, then unzip it to a directory that's already in your system's path. A typical spot for this is user localben. It's where the system automatically searches for executables. You can verify it worked the same way, using Terraform that version. Oh, and a little tip for macOS and some Linux distributions. You can enable autocomplete for Bash or Sesh, using Terraform install autocomplete. It makes typing commands much faster by offering suggestions as you go.
And lastly, let's talk about Linux. Using your distribution's built-in package manager is usually the easiest route here. That's apt for Debian and Ubuntu, Yum for CentOS and RHEL, and DNF for Fedora and Amazon Linux. It's generally a smooth process that integrates well with how you already manage software on Linux.
Definitely. The general steps involve adding HashiCorp's GPG key and the official HashiCorp repository to your system's package sources. That GPG key is like a digital signature. It verifies that the Terraform packages you download are the real deal, no tampering involved. And the repository is essentially the server location where your package manager will find the Terraform software. The exact commands for adding these differ slightly, depending on which flavor of Linux you're using. But luckily, the table in the sources has those specific examples for each distribution.
Once you've got the key and the repository info added, you need to update your package index. Commands like sudo apt update, sudo yum update, or sudo dnf update do that. It's basically refreshing the list of available packages so your system knows about the newly added HashiCorp repository and the Terraform package within it.
And then to install Terraform itself, it's usually a straightforward command, like sudo apt install Terraform, sudo yum install Terraform, or sudo dnf install Terraform. Same as on Windows and macOS. Verify it worked by typing terraform-version. Of course, manual installation is also an option on Linux. Download the zip, extract it into your path, and verify.
That handy table in the sources is a lifesaver here, a quick cheat sheet for all the recommended installation methods and the specific commands you need for each operating system. It's good to keep handy just in case.
For sure. But hey, getting Terraform installed is just the first step. The real magic happens when it interacts with your cloud provider, whether that's AWS, Azure, or GCP, to actually provision and manage your infrastructure.
Yeah.
So naturally, the next step is to set up an account with the cloud provider you plan to use.
And the great thing is all the major cloud platforms have these free tier accounts. They let you explore their services and experiment with Terraform without breaking the bank. The links to their official documentation for setting up those free accounts are mentioned in the sources.
It's worth taking some time to familiarize yourself with your cloud provider's web console and their core services while you're at it. Even a basic understanding of these will make it much easier to understand what Terraform is actually doing for you.
Absolutely. Once you've got your cloud account ready, configuring provider credentials is next on the agenda. This is all about giving Terraform the right permissions to securely talk to your cloud environment. Basically, you're handing it the keys to access and manage your cloud resources. Securely managing these credentials and sticking to the principle of least privilege is super important.
Let's start with AWS. The sources outline a few different ways to set up your credentials. A very common one is using the AWS CLI, the AWS command line interface, specifically the Oz configure command. It walks you through providing your AWS access key ID and secret access key interactively.
You can also go the environment variable route, setting asexeskyid and osakritisesky directly. For Amazon EC2 instances, a more secure method is using IAM roles. That way, the EC2 instance itself takes on a role with the required permissions, so you don't need to embed those credentials directly into your Terraform configurations. And then there's AWS profiles, which live in the .os credentials file. They're great if you juggle multiple sets of AWS credentials. Maybe you're working with different AWS accounts or different IAM roles. Each approach has its pros and cons depending on your needs and how you prioritize security.
Now for Azure, authenticating is usually done through the Azure CLI with the as login command. That typically pops open a web browser for you to log in using your Azure account. Another option is to set environment variables and authenticate with a service principal. Imagine a service principal as a digital identity created just for applications or services. Instead of a person logging in, Terraform uses this application user with specific permissions to interact with your Azure resources. The environment variables for this are ARM cliented, ARM client secret, ARM subscriptioned, and ARM tenanted.
And when it comes to GCP, you can set things up using the Google Cloud CLI and its gcloud init command, which usually involves authenticating through your web browser, similar to Azure. Another common way is to generate and use JSON key files linked to Google Cloud Service accounts. These service accounts in GCP are kind of like those service principals in Azure. They represent non-human identities that can be granted specific permissions within your GCP project. You'll probably also want to set the Google Cloud Project environment variable to tell Terraform which specific GPT project you're focusing on.
Now, across all these providers, a really important security principle that comes up in the sources is the principle of least privilege. It's all about granting just the absolute minimum permissions needed for Terraform to do its job. Don't give it unrestricted access to your entire cloud environment. Limit the potential damage if there's ever a misconfiguration or a security breach.
Couldn't agree more. Minimize that blast radius, contain any potential issues.
Right. Okay, so we've installed Terraform, we've configured our cloud provider credentials. Now we can really start to digging in the heart of how Terraform actually works. Its core concepts and the components that make it all tick.
This is where things get really interesting. At the very core of Terraform, you have the HashiCorp Configuration Language, or HCL. It's the language you use to describe your infrastructure, to write those configuration files we keep mentioning.
What's really neat about HCL is it's designed to be both readable for us humans and structured enough for machines to understand. The sources do point out that while Terraform can handle JSON as well, HCL is much easier to read and write, especially as your configurations grow and you start adding in comments to explain your choices.
HCL is built around three basic building blocks: blocks, arguments, and expressions. Think of blocks as the blueprints for your infrastructure objects. They have a type, like resource, and often a label that you choose, helping you identify them within your configuration. Inside the curly braces of a block, you tell Terraform how to build that specific object.
And that's where arguments come in, right? They're essentially key value pairs, the instructions for building your infrastructure. So if you're setting up an AWS EC2 instance, an argument might be something like AMI 1, 2, 3, 4, 5, 6, 7, 8, and that's telling Terraform which Amazon machine image to use for that instance.
And then we have expressions, which are all about making your configurations dynamic. You can use them to reference variables that you've defined elsewhere, perform simple calculations, or even call built-in functions. A very common example would be instance type equals var.instance type, where that var.instance type is referring to a variable you've declared somewhere in your Terraform configuration.
So just to recap, blocks define the what, arguments specify the how, and expressions add the dynamism.
Exactly. HCL also comes with its own set of data types. The most basic ones, the primitive types, are pretty familiar. Strings, which you put in double quotes, numbers, usually base 10, but you can also use hexadecimal with the 0x prefix, and booleans, which are just true or false.
Then we have collection types. Lists are ordered sequences of values. You put those in square brackets, for example, availability zones, S East 1A, S East 1B. Maps, on the other hand, are collections of key value pairs enclosed in curly braces, often used for tags. Tags name my instance environment dev.
Now, when you're writing HCL, you'll want to use comments to explain what your code is doing. Single-line comments using either hashtag or argo, and multi-line comments enclosed in gel. The hashtag style is generally the preferred way to do it in the Terraform world. Assigning values is done with the standard key equals value syntax. And one thing I really like about HCL is that white space, spaces, tabs, new lines doesn't change how Terraform reads your code, so you can format things for readability.
And to make your strings more dynamic, HCL offers string interpolation using the syntax. You can embed expressions directly into a string, super useful. Say you want to dynamically define a file name based on a module path, you could do file name path.module hello.txt. Those tell Terraform to evaluate the expression inside and plug the result right into the string.
And when you need longer blocks of text, like embedding a user data script for a virtual machine, HCL has you covered with multi-line strings. You use the here doc syntax. Marker, super handy for that.
Now, when it comes to naming things in HCL, your resources, variables, or modules, there are some rules for what are called identifiers. They can be letters, digits, underscores, hyphens, but they can't start with a digit.
Yeah.
Important to remember, HCL is case sensitive, so my variable is different from my variable. HCL files should use UTF-8 encoding, and while different line endings are fine, Unix style, LF, is a preferred way to go.
As with any language, writing clean, well-structured, and easy-to-maintain HCL code is super important, especially for the long-term health of your infrastructure as code. And the sources provide a ton of great advice on this front. A good place to start is consistent naming conventions. A general best practice is to use underscores to separate words and names, so instance type rather than instance type.
And when you're defining variables, give them descriptive names that clearly indicate their purpose. Always specify the type so it's clear what kind of value the variable should hold, and add a clear description explaining its role. This makes it much easier for everyone, including your future self, to understand what your code is doing. A big point the sources make is to parameterize your configurations. Use variables as much as possible instead of hard-coding values into your resource definitions. It makes your code much more flexible and reusable across different environments.
When you're working with larger, more complex infrastructure, good project organization is key. This is where Terraform modules shine, and a well-defined folder structure becomes essential. We'll talk about modules in more detail later, but think of them as a way to group related resources into reusable units. And sticking to the DRY principle, don't repeat yourself by effectively using variables and modules means less code duplication and a much easier time maintaining your code base.
And never underestimate the power of good commenting. Use those hashtag comments liberally throughout your HCL to explain the purpose of each section, clarify any logic that might not be obvious, and document any decisions you've made. And Terraform has some built-in tools to help keep your code clean. The Terraform FMT command automatically formats your HCL according to a consistent style, and Terraform Validate does a static analysis to catch any syntax errors or other issues.
Paying attention to formatting, like using blank lines to separate top-level blocks and nested structures visually, can make your code so much easier to read. And finally, using consistent file naming conventions will add structure and clarity to your Terraform projects. Files like main.tf for your core resource definitions, variables.tf for your variables, outputs.tf for the outputs, providers.tf for provider configurations, and terraform.tfrs for assigning values to your variables.
Okay, we've got a grasp on the language of infrastructure, but how does Terraform actually communicate with our chosen cloud provider and all those other services we want to use? This is where providers come in.
You can think of providers as plugins for Terraform. They bridge the gap between Terraform Core, the main engine of Terraform, and the APIs of different cloud providers and other infrastructure services. They're like specialized translators, letting Terraform speak the language of each platform you want to manage.
And they do a fantastic job of hiding all the complexity of those APIs. They handle all the nitty-gritty details. The sources highlight that providers take care of authentication with the target platform. They understand the different kinds of resources available. They manage the whole life cycle of those resources from creation to deletion, and they make all the necessary API calls to bring your infrastructure into the state you've defined in your code. Basically, you can't manage any infrastructure with Terraform without providers.
It's worth noting that providers have their own release schedule, separate from Terraform Core. That means new features, bug fixes, and updates for a specific cloud provider can be rolled out without you having to upgrade the entire Terraform CLI. When you run Terraform in it, Terraform automatically fetches and installs the specific providers mentioned in your configuration files. These providers are usually found on the public Terraform registry, but in some situations, you might use local registries or even private mirrors.
The sources actually categorize providers into a few distinct types. First, you have the official providers. These are developed and maintained directly by HashiCorp. Think of the big cloud providers like AWS, Azure, GCP, and even Kubernetes. In the Terraform registry, their namespace is always HashiCorp.
Then there are the partner providers. These are built and maintained by third-party companies who are part of HashiCorp's Technology Partner Program. The MongoDB Atlas provider is a good example. Their namespace in the Terraform registry is typically the name of the organization that makes and maintains it.
Then there are the community providers. These come from individual developers or groups within the Terraform community. Their namespace in the registry usually reflects the individual's or organization's account name. While they can be incredibly useful, it's wise to consider their level of maintenance and support from the community before you rely on them. Lastly, we have archive providers. These are providers that are no longer being actively maintained. It's generally best to steer clear of these.
All right, to actually use a provider in your Terraform configuration, you declare it within a provider block, typically in your root module. So for instance, if you want to use AWS in the US East 1 region, you'd write something like this. Provider AWS region, US East 1. The local name, the one you put in quotes like AWS here, usually matches the first part of the resource names it handles, things like AWS instance. Each provider has its own set of configuration options, like the region we just saw for AWS. And those details are all documented for each provider. If you have sensitive config data, API keys, or secrets, the best practice is to use environment variables instead of hard-coding them right into your configuration files.
A cool little feature Terraform offers is the alias meta argument you can use within a provider block. This allows you to configure the same provider multiple times, each with different settings. Say you want to manage resources in 2 different AWS regions, you can create 2 separate provider configurations using alias. Now, while you can set specific provider versions within the provider block itself, the preferred way these days is to use provider requirements.
Right. Inside that main Terraform block, usually in a file called terraform.tf, you define a required providers block. This is where you list the providers your configuration depends on. For each provider, you specify the local name you'll be using, the source address, which tells Terraform where to find it in the registry, for example, HashiCorp for the official AWS provider, and any version constraints you want to enforce. This is considered a better way to handle provider versions because it's clearer and gives you more control over those dependencies.
Now, the central hub for discovering and learning about all these providers is the Terraform registry, found at registry.terraform.io. It's essentially the main repository for public Terraform providers. You can browse and search for providers based on the platform you want to manage, and each provider has its own page with documentation, version info, and even examples of how to use it. When you run Terraform in it, Terraform reaches out to this registry to download the providers you specified. For teams who need to share providers internally, HashiCorp Cloud Platform, HCP, Terraform, and Terraform Enterprise offer the option of private provider registries. The source address for a provider always follows a specific format, hostname and space type. Typically, the default hostname is registry.terraform.io.
Now, to really understand the building blocks of the infrastructure itself, we need to talk about resources.
Resources, well, they represent the actual things you want to create and manage in your infrastructure. That could be virtual machines, storage buckets, network components, databases, you name it. They're the core elements of your infrastructure definition in Terraform.
You define resources using resource blocks within those .tf configuration files we talked about. Each resource block needs 2 pieces of information. A resource type, which tells Terraform what kind of thing you want to create and is specific to the provider you're using, like AWS instance for an EC2 virtual machine on AWS or a REM virtual machine on Azure, and then a local name that you pick, a user-defined name that helps you identify that specific resource instance in your code, like web in resource AWS instance web.
And the details of these resources, how they're configured, that's all done using arguments inside the resource block. These arguments are essentially instructions, sometimes called resource attributes, and they define what you want that resource to look like. Some of these attributes are mandatory, others are optional, and the details are all in the documentation for each specific resource type provided by the provider. The beauty of Terraform is that it handles the entire life cycle of these resources, creating them, figuring out their current state, updating them if needed, and deleting them when they're no longer needed.
Terraform is actually really smart about figuring out dependencies between your resources. It does this based on how you reference them in your configuration. So for example, if you're creating an EC2 instance and you mention a specific virtual private cloud or VPC in its network settings, Terraform understands that the VPC needs to exist before it can put the EC2 instance inside it. Now, in cases where it can't figure that out on its own, or if you need to enforce a specific order of creation or deletion, you can use the depends on meta argument within the resource block.
You might also come across a lifecycle block within a resource definition. This lets you fine-tune Terraform's behavior during certain lifecycle events for a resource. For instance, there's create before destroy, which makes sure that when you update something, Terraform creates a new instance before destroying the old one. It's handy for minimizing downtime. Then you have prevent destroy, a safety net that helps you avoid accidentally deleting a resource. And there's also ignore changes, where you can list specific attributes of a resource that Terraform should ignore when it compares the configured state to the actual state of the resource in the cloud.
Just to give you some examples of common resource types you'll see across the main cloud providers. In AWS, you'll be working with OS instance for EC2 virtual machines, OS3 bucket for S3 object storage, and OS VPC to define your virtual private networks. In Azure, common ones include Azure Virtual Machine, Azure Storage account for handling storage, and Azure Resource Group, which acts like a container for grouping your resources. And over in DCC, you'll likely use Google Compute Instance for VMs, Google Storage Bucket for cloud storage, and Google Compute Network for your network setup. Each resource type has its own set of arguments you'll use to configure it just the way you need it.
Now, as Terraform is busy creating and managing these resources, it needs a way to remember everything about their current configuration. That's where the Terraform state file comes in. It's usually called terraform.tfstate.
This state file is critical to how Terraform operates. It stores a snapshot of your managed infrastructure at a specific moment in time. It's essentially a map, connecting the resources you've defined in your code to their real-world counterparts in your cloud environment. It also tracks all sorts of important metadata and helps improve performance, especially for larger deployments, by caching information about the managed resources.
Terraform uses this state file to figure out what needs to change when you run commands like Terraform plan or Terraform apply. It compares your current configuration with the state file and determines which resources need to be created, updated, or deleted to make sure your infrastructure matches your code. The state file also records crucial details like the unique IDs for each resource, its attributes, and any other metadata from the cloud provider. This gives Terraform a complete understanding of what's been provisioned and how to make changes incrementally in future runs.
That state file also plays a key role in drift detection. Terraform can compare what's in the state file against the actual state of your infrastructure in the cloud to spot any differences. This tells you if something has changed outside of Terraform's control. In team environments, the state file is crucial for state locking. This mechanism prevents multiple people or processes from trying to change the same infrastructure at the same time, preventing conflicts and potential corruption.
Terraform offers two main ways to manage this all-important state: local state and remote state. Local state is the default, meaning your terraform.tfstate file is saved right on your local file system, usually in the same folder as your Terraform config files. It's simple and convenient for testing things out or for solo projects, but it becomes a problem when you're working with a team.
That's because local state means each team member ends up with their own copy of the state file, which can lead to all sorts of confusion. It also introduces security risks, as the state file often contains sensitive information. You don't want to lose it accidentally or have unauthorized access to it. Plus, local state doesn't have built-in versioning or proper backup options, and the sources are very clear on this point. You should never, ever commit your local state file into version control.
The best practice, especially for teams and production environments, is to use remote state. With this, the terraform.tfstate file is stored in a dedicated remote data store. Think Amazon S3 buckets, Azure Blob storage containers, Google Cloud storage buckets, HashiCorp console, or HTTP Terraform's managed state storage. It gives you one single source of truth for your state, making collaboration much smoother and more reliable.
Remote state has a lot of benefits, including better state locking, enhanced security with access controls and encryption, easier backups and recovery, and usually built-in versioning of the state file itself. To set it up, you need to define a backend within the Terraform block of your config. The example in the sources shows how to use Azure Blob Storage as a remote backend, specifying things like the resource group name, storage account name, container name, and the key file name for your state file within that container.
If you peek into the state file, you'll see its structured JSON data. The sources point out some of the key things you'll find: the version of the state file format, the Terraform version that was used to update it last, a serial number that increases with each change, and the values of any outputs you've defined in your Terraform code.
And one of the most important parts is the resources array. This is where all the detailed info about each managed resource is kept: its type, the provider managing it, all its attributes, even sensitive ones, and its current status according to Terraform.
The sources really emphasize several best practices when it comes to managing state effectively. We've already talked about remote state being the way to go for teams in production, as well as enabling state locking whenever your chosen backend supports it. It's also super important to encrypt your state data, both when it's stored and when it's being transferred, using the security features your backend offers.
You also want to take advantage of any versioning your remote backend offers. Put in place proper access controls to secure that backend and back up your state files regularly. This all helps to ensure that your infrastructure state is safe and sound. When things get really big and complex, you might consider isolating state for different environments or different parts of your infrastructure. However, the sources do advise caution when using Terraform workspaces in production. And it's super important to never edit the state file directly. Always use the Terraform state command line tool if you need to make changes. Finally, a good habit to get into is running Terraform refresh often. This syncs your local state with the actual state of your infrastructure, helping you catch any configuration drift.
All right, we've talked about the language, the providers, the building blocks of infrastructure, and that crucial state file. Now let's talk about keeping all that code organized and avoiding writing the same infrastructure definitions over and over again. That's where Terraform modules come in.
Modules are essential for writing good, reusable infrastructure code. They're basically self-contained packages of standard Terraform configurations that you put in their own directories. You use them to group related infrastructure resources that work together for a specific purpose.
Exactly. Modules help you stay DRY. Don't repeat yourself by letting you define a set of resources just once and then reuse that definition multiple times with different configurations. The sources highlight that modules are really the main way you package and reuse configurations in Terraform, and this makes your infrastructure code much more manageable and scalable, creating logical abstractions of your infrastructure components.
Every Terraform setup has at least one root module. This is simply the collection of .tf files in your main working directory where you run your Terraform commands. Now, this root module can call other modules, called child modules, using module blocks in its configuration. And you can call these child modules multiple times within a single root module, super useful for creating lots of similar or identical infrastructure elements.
One of the best things about Terraform is the huge collection of pre-built modules available in the Terraform registry. It can save you a ton of time by providing ready-to-use, well-maintained components for common infrastructure patterns. To use one of these modules, you just declare a module block in your configuration and specify its source and the version you want. The source usually follows a pattern like namespace name provider. The example in the sources shows how to use the official AWS VPC module.
When you run Terraform init, Terraform will automatically download these modules from the registry. Always take the time to read the documentation for any module you plan to use. It will tell you all about the inputs the module expects, what outputs it provides, and any quirks about how to use it properly. To keep your infrastructure stable, the sources strongly recommend pinning your modules to specific versions using the version argument in the module block. This protects you from unexpected changes that might happen if the module gets updated. And for those who need to share modules internally, HashiCorp Cloud Platform, HCP, Terraform, and Terraform Enterprise offer private module registries.
Now, if you want to create your own custom Terraform modules, it's actually pretty straightforward.
It is. You start by creating a new directory for your module. Inside,